Next, purification of colloidal solutions. We know purification is nothing but process used for reducing the amount of impurities to a required level in any particular solution or compound is known as purification. In case of colloidal solution, such technique is called purification of colloidal solutions. One important technique for that is dialysis. What is dialysis? In dialysis, our colloidal solution is kept in one vessel or chamber having a dialyzing membrane, and outside there is a dispersion medium or any clear solution. That's our colloidal solution. Now, because of this membrane, our dialysis membrane allows only electrolytes or the impurities to pass through it, but not the colloidal particles because of their large size. This way, we get rid of impurities from the colloidal solution, but a pure colloidal solution will still remain inside the membrane. This is a dialysis process, and the membranes used may be of animal origin like pig bladder or parchment paper or cellophane sheet. These are certain examples of dialysis membrane. But whatever dialysis we'll do, it's a very slow process. So to do it rapidly, to do it quickly, if we apply electric fluid around that membrane, we can accelerate the purification process, but that will be helpful only if the dissolved impurities in the colloidal solution are only electrolyte, mean they are coulombic charges that can be separated selectively toward electrodes. Like if they are having electrolyte having negative ions, they will move toward the positive electrode, and positive ion will get preferentially toward negative electrode. So these electrolytes, which are small in size, they pass through the membrane, and because of the applied electric field, their separation from the colloidal solution is fast. Exactly the same process is happening here, just like dialysis, but here electric field is increasing the purification. Remember, this is applicable only for impure colloidal solution having electrolytes, because dialysis is slow process. Another purification process known as ultrapurification. Ultrafiltration is separating the colloidal particles from solvent and soluble solutes which are present in colloidal solutions by a special membrane which is permeable to all substances except colloidal particles. Our normal filter paper, if we treat it with collodion is 4% solution of nitrocellulose, which is prepared as a mixture with ether and alcohol. If we pass that or impregnate these collodion in those filter papers, those impregnated filter papers, the pores will be reduced and their size will be such that they allow only electrolytic solute and solvents to pass, but not the colloidal particles. Mean particles having a size greater than 1 nanometer will not be able to pass through it. These such ultrafiltration membranes are created using collodions. properties of colloidal solutions. Colloidal particles are bigger aggregate, which means number of particles in solution is comparatively small in a colloidal solution compared to true solutions. Hence, the value of the colligative properties like osmotic pressure, drop in vapor pressure, depression in freezing points, elevation in boiling points, etc. are of smaller order for colloidal particles or colloidal solution as compared to value of true solutions. So colligative properties of colloidal particles doesn't vary much, like in the case of concentration solutions we saw, because of true solutions they having a large number of particles, their colligative properties vary tremendously with variation in concentration. Now, true solutions, as we discussed, homogeneous mixture of two or more substances in which solute in solvent has a particle size less than 1 nanometer. Let's discuss an important colloidal solution property called Tyndall Effect. What is the Tyndall Effect? It is because of the scattering of light from the colloidal particles in all the directions in space. This scattering of light illuminates the path of a beam in the colloidal dispersion medium. We having the colloidal solution, we pass the light through it. What we saw, because of their size, they scatter the light, and this scattering illuminates the path of light. Homogeneous solutions do appear. We pass the light, there is no effect whatsoever. It will remain effectively like earlier. The path is not illuminated because of true solutions or homogeneous solutions. We can't see anything from right angle. For colloidal solutions, if we observe from a right angle to the path of light, we see clear illumination. So Tyndall effect is a scattering of light by the colloidal particles, by virtue of which its path is illuminated if we view from an angle 90 degree to the path of light. The bright cone of the light is called Tyndall cone. Conditions for the Tyndall effect to occur: the diameter of the dispersed particles and the wavelength of the light that is going to be scattered should be comparable. That's the condition for scattering. And another is the refractive indexes of the dispersion medium and dispersed phase. They should vary. These are the two conditions for Tyndall effect to occur in colloidal solutions. So what is the relation between the colloidal particle size and the color of solutions, colloidal solutions? The color of colloidal solutions depend upon the wavelength of the light scattered by the dispersed particles. The wavelength of the light further depends on the size and nature of the particles. The color of the colloidal solution also changes with manner in which the observer receives the light. For example, finest gold soles is red in color. As the size of the particle increases, it appears purple as we saw earlier, then blue. Small size particle. Color will keep on changing as the particle size will change. ultimately it turns out to be bluish. That's what we see. As a particle size increases, color of the colloidal solution will change. This is because as the size increases, its scattering of light will change. It scatters the light depending upon its wavelength. So whatever the light is scattered, that we view specifically. So here we see larger particles will scatter the wavelength, having larger in what we see like here, this colloidal particles will scatter almost toward the red spectrum, and whatever is left inside it is complementary to it. Another colloidal property is known as Brownian moment. The Brownian movement is due to the unbalanced bombardment of the molecules of the dispersion medium on dispersed particle. These we are showing the larger size, but actually they are on a nanometer scale. These dispersed colloidal particles keep on bombarded by the solution particles. That gives them a random motion nature, and that's why the Brownian movement is a random movement of the colloidal particles in dispersion medium. The reason is unbalanced bombardment by the dispersion medium particles. And that gives them a zigzag path. It depends upon size of the particles and viscosity of dispersion medium. Like Brownian motions, they are not depending upon the colloidal, what collides they are. It may be metallic, non-metallic, or different, but depending only upon dispersion medium viscosity and particle size. Smaller the size, lesser the viscosity, faster is the motion of these colloidal particles.